In our assignment here for implicit second derivatives, we need to be very careful with all of the algebra steps and two substitutions. So you've already seen an example in class, but we'll repeat this so you can come back to review later. Just a note here that we can use y prime, or we can use dy dx, and of course when it was written as an explicit function, we wrote f prime of x. So now we're going to use either the y prime or the dy dx notation, and it would be your choice. All right, so our first equation was written as an equation, not as an explicit function. We're differentiating with respect to x. So our derivative of the x to the fourth term is just a power rule. And our derivative of the y term is 4y cubed, and then we need a chain rule, a derivative of y with respect to x. So either a y prime or a dy dx. The derivative of a constant is 0. So we can solve this for y prime. We would subtract 4x cubed to the other side, and we would divide by 4y cubed. So I think you can all see that the 4's would cancel immediately. And then we're going to take, once you've cleaned up your y prime, we can take that to do our second derivative, and we would use a quotient rule. And the negative, I'm going to bring the -1 coefficient out in front of the derivative. But don't forget, you might need to distribute that later. So I'm going to do low function, y cubed, derivative of the high, 3x squared, minus the high function, x cubed, d low, 3y squared. And don't forget, every time you do a derivative of y with respect to x, you need that y prime or dy dx. And that's all over low squared. And now we can clean this up a little bit, and notice that we have this y prime term here. A derivative doesn't belong within a derivative if we have an alternative. And here we have a very easy alternative, and that's to replace y prime with its equivalent value from our previous step. So now I'm going to do that first substitution, and I can clean up y double prime while I'm at it, perhaps. So I could keep that negative. So we've got a 3x squared y cubed. And our second term is going to be a negative 3x cubed y squared. And here's where our substitution takes place. So this will be a negative x cubed over y cubed. And then we've got some canceling that we can do. So notice that we can cancel y squared here, and it would now leave a y in this denominator. And now always remove the complexity. So we've got a fraction inside the numerator. So if I multiply by y over y, that will clean this up a little bit. So let's see if I can squeeze in another step here. Maybe I'll use another color so it doesn't get too mixed up together. So we have our 3x squared y cubed. And now in our next term, oops, sorry, I forgot to do exactly what I was doing here, multiplying by y. So it's not y cubed, it's y to the fourth. And then here when we multiply, this y will cancel with the y. That was our goal here. And I see a negative times a negative, so this is now a positive term. And it looks like we have 3x to the sixth. And our denominator, notice our denominator is now changed to y to the seventh power. All right, now we're ready to look for one more substitution, and that comes when we factor the numerator. So now in our numerator, let's factor out a 3x squared, and I lost my exponent here. This was a y to the fourth. So I factor out my 3x squared, and we've got y to the fourth plus x to the fourth. And not by coincidence, you want to look for one more substitution. Does this look familiar? Remember our original problem, our original equation said x to the fourth plus y to the fourth was equal to 16. So now we can replace. So always look for the original in your last step. So there's 2 substitution in this process. So now I will have a negative 48x squared over y to the 7th as our final answer for the second derivative. All right, let's see if you can repeat that process. Pause the video if you haven't already tried problem 1, and then you can come back and listen. All right, so first we want to differentiate both sides with respect to x. So I have an 18x by the power rule and a 2y to the first power, and then the derivative, the chain rule of y. And the derivative of the constant is 0. So I want to solve this for y prime. So I'm going to move the 18x to the other side and divide by the 2y. So we know that y prime is negative 9x over y. And let's just keep that negative out in front of the whole thing. So now I'm ready to use my y prime formula to move on to find y double prime. And I'll bring this negative 1 out in front of my quotient rule. And we'll have the low function times the derivative of the numerator is just 9 minus the high function times the derivative of the low function. The derivative of y is just 1 y prime, the chain rule, all over y squared. All right, and here's our first substitution. Remember that this y prime doesn't belong inside of a derivative, so we want to replace this y prime with its equivalent. So now when I do my substitution, we'll have 9y minus 9x times, and here's where we do our substitution of the derivative, negative 9x over y. And then our denominator was badly written. Let's rewrite that, y squared. So now we've got complex fraction because we've got this numerator with a fraction in it. So I'm going to multiply the numerator and the denominator by y. So remember to distribute in your numerator. So now let's clean this up and see what we've got here. And you can distribute this negative sign, or you can still keep it out in front. And notice that this is now going to be a y squared since we're multiplying by y. And here we've got negative times negative, so we've got positive. And this y cancels with this y, so we've got positive 81x squared. And now our denominator is, of course, y cubed. And we look for our second substitution. Can we find the original? Can we find the original expression, 9x squared plus y squared, in our numerator? And that's easy enough to see. If we factor a 9 out of the numerator, there's our x squared plus, our y squared plus 9x squared. So right there it is. So there's our next substitution. This value, we know from the original, can be replaced with 9. So now we get our final answer. Y double prime is going to be negative 81 over y cubed. All right, and let's go again. Try the problem before you watch the video, please. All right, so we're differentiating with respect to x. So hopefully we've done this. You can change this to x to the 1/2, but I know its derivative is 1 over 2 square root of x, and I know the derivative of the square root of y is 1 over 2 square root of y times a chain rule on the y, and our derivative of a constant is 0. So let's clean this up here. Y prime, let's do this in 2 steps here so we don't confuse anyone. So I'm just going to move this term to the other side. You could have multiplied everything by 2 right away. Your choice here how you do this. So I'm just going to subtract this term to the other side. And now to solve for y prime, I'm going to multiply both sides by the reciprocal of this term. So to make this very clear, I'm multiplying both sides now by 2 square root of y. And there, the 2's cancel now if I hadn't canceled them earlier. So our y prime is the square root of y over the square root of x. Negative square root of y over square root of x. All right, so now we've got our y prime. Let's go to our y double prime. And once again, we've got a quotient rule. Let's keep the negative out in front. So we've got low function times derivative of the numerator. The derivative of the square root of y is 1 over 2 square root of y times y prime, the chain rule, minus, so this is our low d high, so now we want a high function, and d low, the derivative of the square root of x is 1 over 2 square root of x. And square the denominator, so that becomes x to the first power, squaring the square root. And like the previous problems, we don't want this y prime here, so we're going to replace it with our y prime value. So let's see what happens when we clean up this fraction. So we've got square root of x over 2 square root of y, and now here is where I'm replacing y prime. So y prime, look at how we're going to be able to do some canceling with that. And then I'm going to go back to the second part here. So we've got square root of y over 2 square root of x, and our denominator is still x. So let's look for some canceling here. So the square root of x, the square root of x, and the square root of y with the square root of y. So our numerator looks like it's just going to be a negative 1 for this first term. So we now have a negative 1/2 for our first term, and a negative square root of y over 2 square root of x for our second term. And we don't like the complex fraction, so let's multiply the numerator and the denominator by 2 square root of x, perhaps. Let's see how that will work out. All right, so remember we're expecting the original function to show back in our numerator. So I'm going to distribute these two terms, and the 2's cancel. So I have a negative, oops, we still have this negative sign out in front, so let's not forget that one. Negative out in front, and now we have this negative sign, the 2's cancel, so we have a negative square root of x. And then here, the 2 square root of x, of course, cancel. So we've got a negative square root of y. And our denominator's a little messier. This is x to the first power multiplied by 2x to the 1/2 power. So let's add those exponents together. So we now have x to the 3/2, or in other words, the square root of x cubed. We'll deal with that later. Notice what we've got here now. We can simplify this negative, distribute that negative, so there's our x squared plus our square root of x plus our square root of y. And our original function told us that that value can be replaced with 1. So there's what we were looking for. So now this becomes our square root of x plus y. That gets replaced with 1. So we're now coming up with this. We can write this as x to the 3/2 if you prefer, or you can write it as 2x square root of x. All the same, your choice. X square root of x, those are equivalent answers. And I hope we made it through that one with no algebra errors. All right, one more time. This time our problem looks a little different. I don't think we need to do a second derivative. We're looking for a tangent line to the circle. So we know that 3, 4, you can verify if you don't believe that this is on the equation. 3 squared is 9, 4 squared for y, 16. So that's how we know this point is on the circle. That's our point of tangency. So now we need to find y prime for our slope. So now we've done this, differentiate with respect to x. We've seen this before. And we got to remember our chain rule on y. The derivative of 25 is 0. And now we can solve for y prime. We would subtract the 2x to the other side. We would divide by the 2y, so the 2's are going to cancel. So this is the slope of all tangents. This is slope of the tangent at any point on the circle. All right, so now we can find y prime such that x is 3 and y is 4. So x is 3 and y is 4. There's the slope of our tangent. So now we know our point of tangency is 3, 4, and our slope is negative 3/4. So the equation of our tangent line. And of course we could also do the equation of the normal if we needed to. And there we have it. Now, let's quickly, before we quit, just look at the geometry. We know what the circle looks like, and we know the point 3, 4 on the graph here. So let's see if you already knew the slope of this tangent from geometry. This point 3, 4 to the origin, 0, 0. So do you see that we already knew that the slope of the radius we would rise 4 and run 3. The slope of the radius, we rise 4 and run 3 to get to this point. And what do we know about the slope of the tangent? The slope of the tangent, because tangent is perpendicular to the radius of a circle. So we could have found this derivative while we were back in geometry. So tangents of circles are the one that we didn't really need to use the derivative formula. But when we're doing ellipses and hyperbolas, then implicit differentiation will be essential.